Surface color and damp. Solar gain. The U.S. Environmental Protection Agency says that for low-rise commercial buildings, the heat gain through the roof is about 50% of the heat gain for the entire building. This heat gain can be reduced not only by using more insulation, but also by reflecting the sun's radiation. The American Society of Heating, Refrigeration, and Air Conditioning Engineers states that the heat gain through a white roof is half of that of a black roof, and the heat gain through a white wall is 2/3 that of a black wall. Thus, in hot climates, the walls should have a light color and the roof should be white. Solar reflectivity, which is also known by the term albedo, is a number that indicates how much of the solar radiation is reflected from a surface. An albedo of 0 indicates that no sunlight is reflected or that all sunlight is absorbed, while an albedo of 1 indicates that all sunlight is reflected. The color white is the highest solar reflectivity with an albedo of about 0.9 if it is fresh, clean, and glossy. Clearly then, the most sustainable buildings would have white roofs and appropriately utilize the colors with an awareness of these aspects. White is the greenest color. When it comes to solar responsive design, choosing white can be the easiest and biggest bang for your buck. Selecting white design elements can save a lot of energy, resulting in saving money and being more efficient and comfortable. White roofs dramatically reduce overheating in both buildings and cities. A white roof will reflect much of the sun's energy, while a dark roof absorbs most of the sunlight and turns it into heat. A dark roof can get more than 60 degrees Fahrenheit hotter than a white roof, significantly heating both the building and the outdoor air. As a result, buildings get heated twice by their dark roofs, once directly through the roofs, and secondly by the increased air temperature of the neighborhood. Cities can be as much as 16 degrees Fahrenheit warmer than the surrounding rural areas due to the extra absorption of dark roofs and pavements and the lack of trees. This heat island effect also increases pollution levels in cities. Rapid deployment of cool materials represents one of the largest and most cost-effective opportunities we have to improve health and strengthen security. U.S. Secretary of Energy Stephen Chu. White buildings can also reduce the energy required for lighting a building. White ceilings and interior walls make electric lighting more efficient, and white roofs and exterior walls can make daylighting more efficient in urban areas. Because daylight enters windows from the sky, most of the light ends up illuminating only the indoor spaces near the windows. On the other hand, much of the light reflected from white walls and the roofs of lower buildings enters windows from below, thereby illuminating the ceiling, which generates better lighting and also sends it farther indoors. White exterior walls also improve nighttime lighting by reflecting, rather than absorbing, street and area lighting. The heat gain through white roofs is 50% less than through very dark roofs, and the heat gain through white walls is about 35% less than through very dark walls. As a result, the use of white not only reduces the amount of energy required to cool buildings, it also reduces the peak electrical load, which occurs in most of the United States on hot, sunny afternoons. Even buildings without air conditioning benefit greatly, because a white roof will result in a ceiling temperature about 3 degrees Fahrenheit cooler. That's equivalent to reducing the indoor temperature about 5 degrees Fahrenheit. Shouldn't roofs be very dark in cold climates to collect solar radiation? The answer is definitely no in any cold climate that experiences overheating in the summer. Thus, white roofs are best in almost all parts of the United States, southern Canada and most of the world. The reason is the asymmetry of solar geometry. For example, at 40 degrees northern latitude, the sun heats a roof for about 15 hours on June 21st, but only about 9 hours on December 21st. The solar heater is on for 6 fewer hours per day in the winter. Also, the low winter sun lights only half of the roof, while the summer sun lights the whole roof most of the day. Furthermore, the wind usually blows more during winter than summer. Thus, a very dark roof loses most of the heat generated to the cold winter wind. Ironically, white roofs make sense even at higher latitudes, because the daylight hours increase in the summer and decrease in the winter. For example, at 50 degrees northern latitude, there are 16 daylight hours for heating on June 21st and only 8 hours on December 21st. Thus, white roofs are best in almost all climates. Black absorbs too much heat. The solar reflection factor, also known as albedo, is shown in the graph for different surfaces colors. Keep in mind that the reflectance factor and the absorption factor are two different ways to describe the same phenomenon. Either can tell us how much of the sunlight falling on a surface is absorbed and how much is reflected. Because white is a very high reflectance factor, the absorption factor must be very low, and with a very dark color, it is the reverse. Because all objects simultaneously absorb and emit radiant energy, their equilibrium temperatures, that is, how hot they get when exposed to the sun, are a result of how much is absorbed compared to how much is emitted. Thus, any object exposed to the sun will simultaneously absorb solar radiation and emit long-wave infrared radiation, which our eyes cannot see but our skin can feel as heat. An object's equilibrium temperature is a function of the solar reflectance and how well it emits heat radiation. The rate at which heat is emitted from an object is a result of both its temperature and its physical ability to emit radiation, which is described by its emittance factor. All colors and surfaces have high emittance except for shiny metal surfaces, which have low emittance. Although shiny metal surfaces reflect most of the solar radiation just as white does, they cannot emit heat radiation as well and, therefore, get much hotter in the sun than do white surfaces. Thus, a white roof will have the lowest equilibrium temperature. A white roof is the coolest roof. Although a very dark color is also a good emitter, it absorbs so much more solar radiation than other colors that it has a very high equilibrium temperature. So why are so many slab roofs dark-colored? A clear and logical reason does not exist. Whatever the reason for dark roofs, most people believe that black is beautiful and white is not. Though when confronted with images like the one on this page, they admit that a white roof need not be ugly. Do people in Bermuda have bad taste because all of their roofs are white? Should we waste money and energy and harm the planet because of widely held opinions and aesthetics? White walls. White walls are already popular, and we know of at least one reason for that. Starting with the Renaissance and reinforced by the neoclassical styles after that, white became popular because it was believed that buildings in ancient Greece and Rome were all white. We are now surprised to discover that parts of ancient Greek temples were painted in bright colors. One objection to the use of white walls is that they cause glare. However, the problem is exaggerated. In the Moroccan city of Casablanca, there is not much glare. Eyes are fully capable of adjusting to slight brightness. We can control much of the potential glare of white walls by planting trees and green walls, which should be done anyway, because they are an important part of creating beautiful cool cities. Only about 50% of the energy in solar radiation is visible. But surfaces exposed to the sun are heated by the full spectrum of solar radiation, which also consists of about 45% solar infrared and about 5% ultraviolet, neither of which is visible to our eyes. Cool coatings. Because of resistance to the use of white or very light colors based on aesthetics, the industry has developed cool colors, or cool coatings. These high-tech color coatings allow the same dark colors to have higher solar reflectances. This apparent contradiction is possible due to the nature of solar radiation. About 50% of solar radiation is visible, about 45% is shortwave infrared, and about 5% is ultraviolet. The color of a surface is determined only by the visible part of the spectrum. Because the cool coatings version of a color reflects more of the non-visible part of the solar spectrum than the ordinary color, the equilibrium temperature is lower. Truth in advertising would require these cool coatings to be called less hot coatings. Although the roof surface's colors graph shows the cool coating versions of various dark colors to reflect more solar radiation than the ordinary versions of those colors, these cool coating colors still reflect much less than white. Thus, they are not the great remedy we are led to believe. Ironically, It is therefore more expensive to get a mediocre benefit by using a cool color than a large benefit from using white or a very light color. Because the coolness of a surface exposed to the sun is a function of both the solar reflectance and the emissivity of the surface, neither of which we can estimate with our eyes, the solar reflectance index was developed to incorporate both. The higher the SRI number, the better. An SRI of 100 represents the performance of a clean white surface, while an SRI of 0 represents a clean black surface. A white roof can reduce air conditioning load as much as 20% in one-story buildings. It can reduce both the initial and the operating costs of the air conditioning system. Adding extra roof insulation in lieu of a white roof is more expensive and is only partially successful, since the dark roof still helps to heat the neighborhood. In homes and other small buildings, the air conditioning ducts are often placed in the attic, where it is common to have 50 degrees Fahrenheit air flowing in the ducts and 150 degrees Fahrenheit air in the attic. This 100 degrees Fahrenheit temperature difference pushes heat through the duct insulation, greatly increasing the air conditioning load. Because they enable smaller, less expensive air conditioning systems, and because it will cost less to cool such buildings, white roofs are a free lunch that you are paid to eat, to borrow from Amory Lovins of the Rocky Mountain Institute. You pay less for them initially to save money for the life of the building. The prejudice against light-colored roofs is a case of how our values can hurt us and the planet. This can be compared to the prohibition against solar clothes dryers. Do those who object believe that dirty laundry is hung out for all to see? Most people hang only their freshly cleaned clothing, so what is the problem? Could it be faulty values? The preference for darker colors for the roofs over white roofs is another faulty value. White is the greenest color text in photos by Norbert M. Lechner via roofs. A cool roof is one that has been designed to reflect more sunlight and absorb less heat than a standard roof. Cool roofs can be made of a highly reflective type of paint, a sheet covering, or highly reflective tiles or shingles. Nearly any type of building can benefit from a cool roof, but consider the climate and other factors before deciding to install one. Cool roofs can be made of a highly reflective type of paint, a sheet covering, or highly reflective tiles or shingles. Standard or dark roofs can reach temperatures of 150 degrees Fahrenheit or more in the summer sun. A cool roof under the same conditions could stay more than 50 degrees Fahrenheit cooler and save energy and money by using less air conditioning. Benefits of cool roofs. Reducing energy bills by decreasing air conditioning needs, improving indoor comfort for spaces that are not air conditioned, such as garages or covered patios, decreasing roof temperature, which may extend roof service life. Beyond the building itself, cool roofs can also benefit the environment, especially when many buildings in a community have them. Cool roofs can reduce local air temperatures, lower peak electricity demand, which can help prevent power outages, reduce power plant emissions, including carbon dioxide, sulfur dioxide, nitrous oxides, and mercury, by reducing cooling energy use in buildings. Types of roofs and how they can be made cool. There are many types of roof systems available, but the surface exposed to the sun is the one that determines if a roof is cool or not. You can usually make a new or existing roof cool by selecting the appropriate surface. Cool roof coatings are white or special reflective pigments that reflect sunlight. Coatings are like very thick paints that can protect the roof surface from ultraviolet light and chemical damage, and some offer water protection and restorative features. Products are available for most roof types. Single-ply membranes are prefabricated sheets rolled onto the roof and attached with mechanical fasteners, adhered with chemical adhesives, or held in place with ballast. How they can be made cool: reformulate or coat black membranes to make them reflective. Built-up roofs consist of a base sheet, fabric reinforcement layers, and a dark protective surface layer. How they can be made cool: the surface layer can be made different ways, and each has cool options, Substitute reflective marble chips or gray slag for dark gravel in a flood coat of asphalt. Use reflective mineral granules or a factory-applied coating rather than a dark coating on a mineral surfaced sheet. Apply a cool coating directly on top of a dark asphaltic emulsion coating. Modified bitumen sheet membranes have one or more layers of plastic or rubber material with reinforcing fabrics, and are surfaced with mineral granules or a smooth finish. These can also be used to surface a built-up roof, known as a hybrid roof. How they can be made cool: pre-coat with a cool roof coating at the factory. Spray polyurethane foam roofs are constructed by mixing two liquid chemicals together that react and expand to form one solid piece that adheres to the roof. Foams are highly susceptible to mechanical, moisture, and UV damage, and rely on a protective coating. How they can be made cool: the protective coatings are usually already reflective, and offer cool roof performance. Shingle roofs consist of overlapping panels made from a variety of materials such as fiberglass, asphalt, wood, polymers, or metals. How they can be made cool: by cool asphalt shingles, which use specially coated granules that provide better solar reflectance. Coating existing asphalt shingles to make them cool, however, is not normally recommended or approved by shingle manufacturers. Other roof shingles can be coated at the factory or in the field to make them more reflective. Tile roofs can be made of clay, slate, or concrete. Tiles can be glazed to provide waterproofing or coated to provide customized colors and surface properties. How they can be made cool: some are naturally reflective enough to achieve cool roof standards, and surface treatments can transform tiles with low solar reflectance into cool roof tiles. Metal roofs are available with natural metallic finishes, oven-baked paint finishes, or granular coated surfaces. How they can be made cool: unpainted metals are typically good solar reflectors but poor thermal emitters, so they rarely satisfy low-slope cool roof requirements. Painting a metal roof can increase its solar reflectance and thermal emittance, allowing it to achieve cool roof status. Alternatively, you can apply cool reflective coatings. Green roofs. You may also consider installing a green roof. Green roofs are ideal for urban buildings with flat or shallow pit roofs, and can include anything from basic plant cover to a garden. The primary reasons for using this type of roof include managing storm water and enjoying a rooftop open space. Green roofs also have some insulate properties, lower the need for heating and cooling, and can reduce the urban heat island effect. This roof type can be much more expensive to implement than other efficient roof options. Deciding whether to install a cool roof. When deciding whether to install a cool roof, you'll need to determine whether the cost will justify the energy savings. How much energy you will save depends on several factors such as your home's climate and environment, how well insulated your current roof is, the type of roof you have, and the efficiency of your heating and cooling system. If you are building new, you can decide during the planning phase what type of roof to install and whether it should be a cool roof. If you want to convert an existing roof into a cool roof, you have three basic options: retrofit the roof with specialized heat-reflective material, recover the roof with a new waterproofing surface, replace the roof with a cool one. If the roof is in poor condition or near the end of its life, it is usually best to recover, replace, or retrofit the roof. Cost and energy savings. A cool roof does not necessarily cost more than a non-cool roof, especially if you are installing a new roof or replacing an existing one. However, converting a standard roof that's in good condition into a cool roof can be expensive. Major roof costs include upfront installation and ongoing maintenance. Additional cool roof costs include specialized materials and labor. Cool roofs can save money in several ways, including energy savings, rebates and incentives, HVAC equipment downsizing, and extended roof lifetime. One way to estimate how much energy you would save by installing a cool roof is by using the roof savings calculator at climate and environment. Your climate is an important consideration when deciding whether to install a cool roof. Cool roofs achieve the greatest cooling savings in hot climates, but can increase energy costs in colder climates due to reduced beneficial wintertime heat gains. Moisture control. In warm, moist locations, cool roof surfaces can be more susceptible to algae or mold growth than hot roofs. Some roof coatings include special chemicals that prevent mold or algae growth for a few years. In cold climates, roofs can accumulate moisture through condensation, and it is possible that cool roofs might be more susceptible to accumulating moisture than dark roofs of the same design. Condensation can be avoided using proper design techniques.